According to scientists, the history of the universe unfolds with the Big Bang, an infinitesimal speck of energy that erupted and expanded into the universe as we know it today. However, have you ever pondered what existed before this monumental event? Recent discoveries suggest that scientists may have uncovered compelling evidence hinting at the existence of a prior universe that predates our own. They speculate that our universe might simply be one in a sequence of universes spanning eons. But do these claims hold up under scrutiny? To delve deeper into the period preceding the Big Bang, join us as we investigate. Scientific consensus tells us that our universe originated from the Big Bang approximately 13.8 billion years ago. At that moment, an extraordinarily dense and scorching speck of energy, occupying an incredibly minuscule space, underwent a cataclysmic explosion, giving birth to the first atoms. This event marked the genesis of the observable universe, which then expanded over countless eons into the cosmos we observe today. Up to this point, scientists have managed to trace evidence of the Big Bang only to fractions of a second after its occurrence. The enigma of what caused the Big Bang and what preceded it has remained elusive. However, this narrative might be evolving. Theoretical physicist and Nobel Prize laureate Sir Roger Penrose has advanced a theory proposing that our universe did not arise from nothingness but rather emerged as a consequence of a previous universe. Sir Roger Penrose enjoys an esteemed reputation as both a mathematician and physicist, having made significant contributions to the fields of general relativity and cosmology. His accolades include sharing the Wolf Prize in Physics with Stephen Hawking in 1988 and being awarded half of the Nobel Prize in Physics in 2020 for his groundbreaking revelation that black hole formation is a robust implication of the general theory of relativity. His theories hold a prominent position within the scientific community, reflecting the high regard in which he is held. Within the scientific community, when Sir Roger Penrose introduced his theory about the universe's origins, it ignited a wave of astonishment. In his book, A Cycle of Times, Penrose put forward what he termed the conformal cyclic cosmology model. This model, a branch stemming from Einstein's general relativity, diverged significantly from Einstein's initial hypotheses. Penrose's cosmological model deviated from the commonly embraced multidimensional theories, instead proposing that the universe exists in distinct phases, contradicting the prevailing multiverse concept. His theory was based on his observations of concentric circles, which he discerned while examining both past and present versions of the cosmic microwave background, CMB. According to Penrose, his observations led him to conclude that a previous universe may have existed before the Big Bang, which gave birth to our own universe. In his book, he asserted that the Big Bang was the outcome of the concluding stages of this pre-existing universe, a universe that had eventually contained only evaporating black holes, absorbing all cosmic matter within its bounds. Penrose contended that, at the conclusion of this universe, all matter had condensed into these evaporating black holes, essentially transforming into photons that existed outside the confines of space and time. In his view, these photons bore striking similarities to the initial photons observed in the first few milliseconds of the Big Bang. Consequently, the singularity responsible for the Big Bang was equated with the infinitely expanded pre-existing universe. Penrose's theory stemmed from an examination of the cosmic microwave background, CMB, the earliest electromagnetic radiation that permeated the early universe. Known among physicists as relic radiation, CMB is ubiquitously distributed throughout the cosmos and serves as a vital source of data, offering insights into the thermal radioactive state of the early universe. CMB dates back to the epoch when the very first atoms formed, a phase referred to as recombination, approximately 375,000 years after the Big Bang. While this might appear to be an extensive period, in the larger context of the observable universe, it remains relatively brief. Nevertheless, it provides the most proximate insight into the early universe's conditions. The cosmic microwave background, CMB, is the medium through which we glean this understanding, and it is observed through radio telescopes. These instruments reveal a subtle luminescence within the voids amidst stars and galaxies, detached from any other celestial entities. Sir Roger Penrose harnessed CMB data to advance his findings. Essentially, The CMB functions as a snapshot of the early universe, a juncture at which temperatures had declined sufficiently to permit the formation of hydrogen atoms from protons and electrons. In their published analysis of the cosmic microwave background data, Penrose, in collaboration with 3 other researchers, Christoph and Tony Meissner, Daniel Ann, and Pavel Narowski, unveiled the presence of peculiar points in their observations. These points contributed fresh insights to our understanding of cosmology. Their conjecture posited that these anomalies could potentially be vestiges of signals or energies emanating from supermassive black holes that existed in the universe preceding ours. They attributed these points to the actions of evaporating supermassive black holes because black holes are the sole entities in the entire universe capable of withstanding and generating energy at a density comparable to the Big Bang's magnitude. Penrose contended that his analysis of the CMB data provides initial evidence for the collision of supermassive black holes in a pre-existing universe. This hypothesis gained support from the fact that these black holes were the only structures powerful enough to impart gravitational wave ripples during the early stages of our own universe. In buttressing his theories, Penrose scrutinized the practical implications of the second law of thermodynamics in relation to the universe's ultimate state. While his perspective draws significantly from contemporary theoretical physics, it diverges from the viewpoint of Stephen Hawking, who asserted that information is annihilated when matter or energy enters a black hole. Interestingly, Penrose isn't alone in challenging the notion that black holes are mere cosmic voids engulfing energy within the universe. Instead, he posits that they break down energy into photons that exist beyond the confines of space and time, residing beyond the event horizon. According to Penrose's perspective, these photons, existing beyond the constraints of space and time, could serve as the fundamental building blocks for a subsequent universe, triggering a Big Bang event. He further proposes that, over incomprehensible spans of time, potentially trillions of years, all matter within the observable universe undergoes this transformation into photon energy in an expansive, frigid universe. He refers to this period, extending from one Big Bang to the boundless expansion of a universe, as an eon. The infinite expansion and ultimate dissolution of the preceding eon serve as the foundational elements for the Big Bang inception of the next eon cycle. This crucial juncture, bridging the conclusion of one eon and the inception of another, renders space and time irrelevant, presenting the commencement of a new eon as relatively diminutive when perceived by its inhabitants. Penrose also posits that the singularity commonly associated with the Big Bang may not be as enigmatic as once believed. He suggests the presence of similar singularities at the event horizons of black holes. He contends that the circular streaks observed in the cosmic microwave background, CMB, represent highly redshifted photons, originally within black holes of the previous universe, finding their way into our existing universe. While these circle streaks on the CMB may appear inconspicuous to the layperson, they hold substantial significance to physicists, carrying remnants of low-energy cosmic energy from a prior universe. Penrose's theory posits that the cosmic energy engulfed by black holes in a previous epoch can become linked to the future Big Bang of the subsequent eon, following an inconceivable period of cosmic expansion. Penrose's theory, forecasting the universe's end through infinite expansion, not only aligns with his hypothesis of a prior universe but also directly contradicts one of the prevailing theories regarding the universe's demise, the Big Crunch. Until now, cosmologists have advanced the idea that the universe's ongoing expansion was merely a phase, with gravity's attractive force among cosmic matter eventually decelerating the expansion rate as the universe aged, eventually leading to a gravitational pull that would bring all entities together. The Big Crunch theory once posited that the ultimate destiny of the universe would be determined by the gravitational forces exerted by all the celestial masses within the cosmos. This scenario would eventually culminate in a cosmic-scale contraction, signifying the universe's ultimate collapse. This cataclysmic crunch would be incredibly dense and intensely hot, capable of triggering another Big Bang, thereby initiating a new universe. While this idea of one universe's end giving rise to the birth of another bears some resemblance to Penrose's theory, there is a critical discrepancy. The expansion of the universe, as supported by current astronomical evidence, does not align with the Big Crunch theory. Contrary to the notion that the universe's expansion is slowing down due to gravitational forces, observations indicate that the expansion rate is, in fact, accelerating. The data demonstrates that distant stars and galaxies are receding from our Earth-based telescopes at an increasing pace over time. This discovery was further substantiated through the study of supernovas, which provided compelling evidence that the universe's expansion is not constant, as previously believed. Consequently, this rapid expansion discredits the Big Crunch theory, as gravitational forces seem to have no discernible influence on the cosmic expansion, let alone its potential collapse. This mounting evidence reinforces Penrose's assertion that the universe will perpetually expand until even black holes disintegrate into photons, paving the way for the birth of a new universe and the commencement of another eon. While Penrose's theory remains a subject of vigorous debate within the scientific community, he has ventured into more controversial territory involving extraterrestrial life, not only within our universe but in the universe that preceded ours. Penrose introduces the Fermi paradox, a hypothesis with a scarcity of supporting evidence but a high degree of plausibility in the context of cyclic cosmology and the concept of a pre-existing universe. In this paradigm, Penrose proposes that the potential for information transfer between different eons is feasible. His study of the cosmic microwave background, CMB, leads him to speculate that advanced civilizations might encode intelligent signals within gravitational wave functions, transcending eons and passing information to other civilizations in subsequent universes. While this notion is hotly debated within the scientific community, with other researchers exploring the CMB in search of corroborating evidence, it remains uncertain whether they will arrive at the same conclusions as Penrose. In conclusion, the question of whether a universe existed before our own or whether traces of trans-eon information exist remains unproven. What is indisputable is that we have our own universe to explore and comprehend before delving into the concept of a prior universe. The possibility of a past universe, and perhaps even a past Earth, remains a topic of intrigue and ongoing exploration. Feel free to share your thoughts in the comments and stay tuned for our next video.